Hello, friend. Welcome back. Or if this is your first time drifting with us, welcome home. Some nights the world feels wider than it should. Stars breathe slower. Time folds in silence. Maybe that's just the mind listening to itself. But tonight, there's something else. Something quieter than a question, softer than wonder. Have you ever looked up and noticed one star seem brighter than it was before? Or maybe dimmer, like it's breathing. Like something ancient is remembering how to pulse. Most stars hold steady, Polaris, Sirius, Vega. Night after night they anchor the dark. But some stars flicker, some fade. Some burst into brilliance and then retreat as if the universe itself is exhaling. And for thousands of years, we didn't know why. We just watched, confused, curious, sometimes afraid. Before we begin this quiet journey together, if you find comfort in these slow stories, told softly, you might like to stay a while. You can gently tap the like button, subscribe if you'd like more nights like this, and ring the little bell, not for noise, but so the next quiet story can find you again when you need it most. No pressure, just an invitation. Now, let's drift. Tonight we'll move gently into a mystery that began long before telescopes, before equations, before we even had words for what we were seeing. We'll walk through the eyes of ancient stargazers who first noticed something strange, something that shouldn't have been possible, because in their world, the heavens were supposed to be perfect, unchanging, eternal. And then one night, a star that had always been there wasn't. Or a star that had never existed suddenly appeared blazing brighter than anything around it. You don't need to understand everything, just rest. Let curiosity do the listening. And if your mind begins to wander, that's okay. Sometimes the best way to learn is to drift. The story begins not in a laboratory, not in a university, but on a rooftop in ancient Greece. The year is 129 BC. A man named Hipparchus stands in the cooling evening air staring upward. He's been doing this for years, cataloging, counting, measuring positions. He knows the sky the way you might know the face of someone you love, every detail, every freckle of light. And tonight something is wrong. There's a star, bright, shining where no star should be. He checks his records. Nothing. He checks again. Still nothing. This star burning clearly in the constellation, Scorpius, had never been there before. Or if it had been invisible, too faint to see. And now it glowed like a small sun, visible even in the twilight. Hipparchus didn't have the language we have now. He couldn't call it a supernova or a cataclysmic variable. He just called it what it seemed to be. Stella nova, a new star. And that single observation, that one moment of seeing something impossible, would haunt astronomy for the next 2,000 years. Because if stars could appear, if the heavens could change, then maybe the universe wasn't as eternal as everyone believed. Maybe even the stars had a story, a beginning, an end, a breath. But Hipparchus was alone in noticing. Most people didn't look up the way he did. They saw patterns, mythologies, gods frozen in constellations. They didn't see the light itself, so his catalog, his careful list of 850 stars and their positions, became one of the most important documents in human history. Not because it answered questions, but because it was the first time someone treated the stars like they could change, like they were real. Centuries passed. The observation faded into scholarly footnotes. And then, on a cold November evening in 1572, the sky split open again. Tycho Brahe, a young Danish astronomer with a metal nose and a reputation for brilliance, stepped outside after dinner. He glanced up as he always did, and stopped, frozen. There, blazing in the constellation, Cassiopeia was a star so bright it was visible in daylight. Magnitude -4, brighter than Venus, brighter than anything except the sun and moon. A star that absolutely unquestionably had not been there the night before. Tycho didn't sleep that night, or the next. He measured, he triangulated. He checked for parallax, the slight shift that happens when you view something close from different angles. Nothing. The star was far beyond the moon, far beyond the planets. It was truly a star, and it was new, or at least newly visible. For 18 months, Tycho watched it, recorded its brightness every single night, watched it slowly dim, from brighter than Venus to barely visible to gone, completely gone, swallowed back into the dark. And when it vanished, it left behind something more unsettling than its appearance. It left behind doubt. Because according to Aristotle, according to the church, according to everyone who had ever thought seriously about the cosmos, the heavens were supposed to be unchanging, perfect spheres turning in perfect circles for all eternity. But here was proof written in light that stars could be born and stars could die. We know now what Tycho saw. We call it SN 1572, a type Io supernova about 7,500 light-years away. A white dwarf star stealing matter from a companion until the mass became too great, and the whole thing detonated in a thermonuclear explosion so bright it could be seen across the galaxy. But Tycho didn't know that. He just knew the universe had lied to him, and he spent the rest of his life trying to understand how. But the story we're drifting toward tonight isn't just about stars appearing and disappearing. It's about something stranger, something more subtle. Stars that don't vanish, stars that just breathe, that dim and brighten over and over again in rhythms so precise you could set a clock by them. And the first person to truly see this, to recognize it for what it was, wasn't a famous astronomer with a brass telescope and royal funding. It was a deaf boy in England who couldn't hear a single word, but could see the sky more clearly than almost anyone alive. His name was John Goodricke. He was born in 1764 in Groningen, Netherlands, though he would spend most of his short life in York, England. Scarlet fever in early childhood had left him profoundly deaf. In that era, many considered deafness a kind of intellectual disability, but Goodricke's mind was sharp as winter air. By the time he was 18, he was already obsessed with the stars. Not the mythology, not the astrology, the actual physical light. And one night in November 1782, while observing the constellation Perseus, he noticed something strange about a star called Al-Gol. The Arabs had called it Ras al-Ghul, the demon's head. The Greeks called it the Gorgon's eye. Even its name carried unease, and Goodricke saw why. Every 2 days and 21 hours, like clockwork, Al-Gol dimmed, not by a little, by 70%. For about 10 hours, it faded from second magnitude to third, then slowly climbed back to full brightness. And then 2 days later, it did it again. Perfectly, predictably, mechanically. As if something in the universe had a pulse, as if the star itself was blinking. Most astronomers before Goodricke had noticed this, but dismissed it as observational error, or atmospheric distortion, or maybe just tired eyes. But Goodricke kept watching. Night after night through the freezing York winters, he recorded every variation. And then he did something extraordinary. He proposed a theory, not magic, not myth, science. He suggested that Al-Gol might not be one star, it might be two. A binary system with one star orbiting in front of the other, blocking its light like a miniature eclipse. Every 287 days, the dimmer star passed in front of the brighter one. And from Earth, we saw a dip in brightness. Not because the star was changing, but because something was in the way. Geometry, not magic. Prediction, not superstition. He was 18 years old, deaf, working without formal institutional support, and he had just solved a mystery that had puzzled humanity for centuries. The Royal Society awarded him the Copley Medal in 1783, the highest honor in British science. He was the first person to correctly explain a variable star, the first to prove that stars could change brightness in regular, predictable ways, the first to turn the demon into mathematics. But here's the part that makes you stop, the part that sits heavy in the quiet. John Goodricke died 2 weeks after announcing his discovery of another variable star, Delta Cephei. He was 21 years old. Some historians think it was pneumonia brought on by too many freezing nights spent observing the sky. Others think it was an infection, something sudden. We don't know. We just know that the boy who couldn't hear spent his short life listening to the stars in a way no one else could. And in doing so, he changed how we see the universe. Before Goodrick, stars that dimmed or brightened were omens, demons, signs from gods. After Goodricka, they became phenomena, things that could be studied, measured, understood. He turned fear into curiosity. And in doing that, he opened a door. Because once we knew stars could vary, once we understood that the sky itself was not frozen, but alive, breathing, pulsing, then we had to ask the next question. Not just which stars change, but why. What makes a star brighten? What makes it dim? Is it distance chemistry, gravity age? And more than that, what does that rhythm mean? Can we read it like a language? Can a star's pulse tell us how far away it is? How old? How much longer it has to live? These aren't just academic questions. They're the questions that would eventually let us measure the size of the universe. That would show us we live in an expanding cosmos. That would reveal the life cycles of stars, from birth in nebulae to death in supernovae and everything in between. All of that started because a deaf boy in York noticed a demon star didn't stay the same. So, tonight as we drift deeper into this quiet mystery, we're not just learning about stars, we're learning about seeing, about noticing, about how sometimes the most important discoveries come not from the loudest voices, but from the quietest ones, from people who watch, who wait, who let the universe speak first. And what the universe is saying in its slow and patient way is this: nothing lasts forever. Not brightness, not darkness, not even the stars. Everything pulses, everything changes. And that's not chaos, that's not decay, that's life. Even out there in the cold and the black and the silence, life finds a way to breathe. So now we've met the watchers, the ones who first saw that stars were not eternal jewels, but living things, breathing things. And now we can begin to ask the deeper question. Not just that stars change, but how and why, and what that breath, that cosmic inhale and exhale can teach us about the nature of light time and everything that burns. Imagine a heart beating in slow motion across light years. Each pulse takes days, sometimes weeks. The rhythm is so vast, so patient, that a single heartbeat could span your entire childhood. And yet, it never misses, never falters. Just breathes in and out, swelling and shrinking bright and dim for thousands, sometimes millions of years. This is what some stars do. They don't just shine, they pulse. And the story of how we learn to hear that pulse is one of the most beautiful accidents in the history of science. We left John Goodrick watching Algol solving the mystery of eclipsing binaries. But he discovered something else before he died, another variable star. This one wasn't dimming because something passed in front of it. This one was changing all on its own, swelling, contracting, breathing. He called it Delta Cephei, named for its position in the constellation Cepheus. And he had no idea he'd just found the key to measuring the entire universe. Delta Cephei sits about 887 light-years from Earth. To the naked eye, it looks like an ordinary star, maybe a little brighter than most. But if you watch it carefully night after night, you'll notice something strange. Every 566 days, like clockwork, it brightens. Its luminosity doubles, then just as steadily it fades back down. And then it does it again. 5.366 days. Not 5.3, not 5.4, 5.366. You could set your calendar by it. And for over a century after Goodrick's death, no one understood why. The breakthrough came from an unexpected place, not a grand observatory with marble halls and brass telescopes, but a small brick building at Harvard College Observatory, where a group of women hired as human computers sat at wooden desks analyzing thousands of photographic plates of the night sky. They weren't given titles. They weren't called astronomers. They were paid 25 cents an hour, and one of them, a woman named Henrietta Swan Leavitt, was about to change cosmology forever. Leavitt was born in 1868 in Lancaster, Massachusetts. By the time she joined the Harvard computers in 1893, an illness had left her partially deaf. Sound familiar? Like Good Ricky, she couldn't hear the world the way most people did, but she could see patterns. And in 1908, while studying photographic plates of the small Magellanic Cloud, a dwarf galaxy orbiting our own, she noticed something no one else had. The small Magellanic Cloud contains thousands of Cepheid variable stars, stars like Delta Cephei, stars that pulse. And because they're all roughly the same distance from Earth, about 200,000 light years away, Leavitt could compare them directly. And what she saw made her stop. The brighter a Cepheid was, the longer its period. A Cepheid that pulsed every 3 days was dimmer than one that pulsed every 30 days. The relationship was perfect, mathematical, predictable. She published her findings in 1912. The paper was short, modest. She called it a period luminosity relationship. But what it meant was staggering. If you could measure how long a Cepheid took to pulse, you could calculate its true brightness, its absolute luminosity. And if you knew how bright it actually was versus how bright it appeared from Earth, you could calculate exactly how far away it was. Suddenly, Cepheids weren't just interesting variables. They were cosmic rulers, standard candles, distance markers scattered across the universe. Within a decade, Edwin Hubble would use Leavitt's discovery to prove that the Andromeda Nebula wasn't a nebula at all. It was a galaxy, a separate island of stars millions of light years away, and the universe, which we thought was just the Milky Way, suddenly became infinite. All because Henrietta Leavitt noticed a pattern in the breathing of stars. But here's what makes it even more beautiful. She never got to see what her discovery became. She died in 1921 at age 53 from cancer. No Nobel Prize, no statue, no public recognition in her lifetime. Just a footnote in a Harvard circular and a modest obituary. And yet, every time we measure the distance to a far galaxy, every time we calculate the expansion rate of the universe, every time we talk about how old or how large the cosmos is, we're using her work, her pattern, her patient observation of stars that breathe. So, what makes a Cepheid pulse? Why does it swell and shrink like a beating heart? The answer is a dance between gravity and pressure. Heat and light played out in layers of gas, hundreds of times larger than our sun. Scientists call it the Kappa mechanism, though the name doesn't quite capture the beauty of what's happening. Deep inside, a Cepheid hydrogen fuses into helium, releasing energy. That energy pushes outward, trying to escape. But surrounding the core is a layer of helium partially ionized that acts like a blanket. When the star contracts, this helium layer heats up and becomes more opaque, trapping energy inside. Pressure builds, temperature rises, and eventually the trapped energy pushes back so hard the entire star swells. The outer layers expand, cool, become transparent, and the energy escapes. Without that pressure, gravity pulls everything back inward. The star contracts, and the cycle begins again. It's not chaos, it's resonance, like a bell ringing at its natural frequency. The star finds a size where compression and expansion balance perfectly, and it locks into that rhythm. Some Cepheids pulse every few days, some every few weeks, but once they find their rhythm, they hold it for millennia. Through the rise and fall of civilizations, through ice ages and warm periods, through the entire span of human history, the star just breathes. And we've found thousands of them now. Classical Cepheids like Delta Cephei, Type II Cepheids, which are older metal poor and follow a slightly different period luminosity relationship. We've found them in our galaxy, in nearby galaxies, even in galaxies billions of light years away. Each one a lighthouse, each one a cosmic metronome marking time and distance across the void. But Cepheids aren't the only stars that pulse. There's another class, older, fainter, more common. They're called RR Lyrae variables, named after the first one discovered in the constellation Lyra. And if Cepheids are the steady heartbeat of young massive stars, RR Lyrae stars are the faint, tired pulse of the old. RR Lyrae stars are smaller than Cepheids, less luminous, but they pulse faster, periods of half a day to a day. And because they're older, because they've burned through more of their fuel, they're found in different places. Not in the spiral arms of galaxies where stars are being born, but in globular clusters, those ancient spherical swarms of stars that orbit galaxies like moons. Some of the oldest structures in the universe, and the RR Lyrae stars inside them are ticking clocks telling us how old those clusters are, how long ago they formed, how the early universe structured itself. Imagine that. A star's pulse, its simple in and out breathing, can tell you not just how far away it is, but how old, how much metal it contains, where it was born, what generation of star it is. It's like reading a biography written in light, and the more we listen, the more we learn to hear. Because here's the thing. When John Goodricke first saw Delta Cephei pulse, he didn't know what he was looking at. When Henrietta Leavitt found the period luminosity relationship, she didn't know she was measuring the universe. They just watched, recorded, noticed, and trusted that if they looked carefully enough, long enough, patiently enough, the stars would tell them something true. And they did. The stars said, "We are not fixed. We are not eternal. We change. We pulse, we breathe, and if you learn to read our rhythm, we will show you distances you can't imagine, ages you can't fathom, structures too vast for your eyes. All you have to do is watch." Scientists today still use Cepheids. The Hubble Space Telescope has observed Cepheids and galaxies over 60 million light years away. The James Webb Space Telescope is pushing even further. And every observation refines what we know. Every pulse adds another data point to the great map of cosmic distances. Because as long as stars breathe, we can measure. As long as they pulse, we can see. But even now, there are mysteries. Some Cepheids pulse irregularly. Their periods drift slightly over decades, and we're not entirely sure why. Some seem to pulse in two modes at once, like a heart with an arrhythmia. Some are in binary systems orbiting companions, and the interaction changes their behavior in ways we're still untangling. The more we learn, the more complexity we find. And that's not frustrating. That's the point. Because science isn't about having all the answers. It's about asking better questions. And stars that pulse are asking us to look closer, listen harder, be patient. Have you ever felt your own heartbeat? Really felt it, not just noticed it, but focused on it. The steady thump, the pause, the next thump. It's easy to take for granted, but every beat is a collaboration between electricity, chemistry, muscle, and pressure. A rhythm your body found in the womb and has held ever since. And out there in the dark, stars are doing something similar, pulsing, holding rhythms that began millions of years ago and will continue long after we're gone. So, when you look up tonight, if the sky is clear, find Polaris, the North Star. It's a Cepheid variable, not a dramatic one. Its brightness changes by only about 15% over 4 days. But it's there, breathing quietly, faithfully. And every pulse is a reminder that even in the vastness, even in the cold, even across distances so great light takes centuries to cross them, there is rhythm, there is pattern, there is something like a heartbeat. And that brings us somewhere new, because not all stars pulse gently, not all rhythms are steady. Some stars don't breathe, they eclipse, they hide. They pass in front of each other like dancers in the dark, and for a few hours their light dims, not because they changed, but because something came between us and them. Two stars waltzing so close, their light becomes a shared breath. And every few days, like clockwork, one passes in front of the other. For a handful of hours, the brightness dims. Not because anything changed inside the stars themselves, but because from where we stand from our small blue planet orbiting an average sun, we're watching geometry, shadow play, a cosmic eclipse happening so far away that the light we see left those stars before you were born, before your grandparents were born. And yet, we can see it. We can measure it. We can know with absolute certainty that those two stars are dancing. This is the world of eclipsing binaries. And the first person to truly understand what was happening, as we've already met, was John Goodrick. But the star he studied, the one that earned him a place in history, deserves its own story. Because for thousands of years before Goodrick pointed his telescope at it, people feared this star. They called it the demon star, Ras al Ghul, the Ghoul, and they had no idea they were watching one of the most beautiful partnerships in the night sky. Algol sits in the constellation Perseus the hero who slayed Medusa, and in most depictions, Algol marks Medusa's eye, the Gorgon's gaze, the thing you're not supposed to look at directly, or you'll turn to stone. Ancient astrologers considered it the most unfortunate star in the heavens. They said it brought misfortune, violence, sudden death. And maybe they felt that way because, unlike every other star around it, Algol blinked. Every 2 days and 21 hours it dimmed, for about 10 hours. And then it came back, like an eye closing, like something alive. Goodrick proved it wasn't magic, it was geometry. Algol isn't one star, it's 3. A tight system 93 light-years from Earth. The brightest Algol A is a blue-white main sequence star about 3 times the mass of our Sun. Algol B is dimmer cooler, an orange subgiant about 0.8 solar masses. And there's a third companion Algol C orbiting farther out. But the magic, the dimming that terrified ancient stargazers comes from the dance between A and B. Every 2.867 days, Algol B passes directly in front of Algol A from our perspective. It blocks about 80% of the brighter star's light. The system's total brightness drops from magnitude 2.1 to 3.4. That's a reduction of about 70%. For 10 hours, the demon star dims. And then, as Algol B moves past, the light returns. Perfectly, predictably, like breath. But here's where the story gets strange. Algol B, the dimmer star, is larger than Algol A, the brighter one. That shouldn't be possible. In normal stellar evolution, more massive stars evolve faster. They swell into giants first. But in Algol, the less massive star is already a subgiant, while the more massive one is still on the main sequence, still fusing hydrogen in its core. For decades, astronomers called this the Algol paradox. How could the smaller star be older? The answer is mass transfer. Algol B used to be the more massive star. It evolved first swelled into a giant and began losing its outer layers, but it wasn't alone. Algol A was close enough that its gravity pulled material away from B, stealing it, atom by atom. Over millions of years, Algol B lost most of its mass. It shrank, became dimmer, while Algol A grew heavier, brighter, younger in a sense because it had been fed. So now we see a massive bright star orbiting a smaller, older companion, a reversal, a theft, a cosmic cannibalism happening so slowly, we can only see the result, not the act itself. This process is called Roche-Lobe overflow. Every star in a binary system has a region around it where its gravity dominates. That region is called the Roche-Lobe. If a star grows large enough to fill its Roche-Lobe, material spills over into the companion's gravitational influence. And once that transfer begins, it's hard to stop. The losing star keeps shrinking. The gaining star keeps growing until something breaks, until one star dies, or until they merge entirely. In some systems, the transfer is gentle, slow, a trickle of gas flowing from one star to another over millions of years. In others, it's violent, explosive. The material crashes into the companion so hard, it forms an accretion disk, a swirling vortex of superheated gas that glows brighter than the stars themselves. And in a few rare systems, the transfer happens in bursts. The material builds up, ignites, and explodes in a nova. But we'll get to those later. For now, let's stay with Algol. Because even though we've solved the paradox, even though we understand the mechanics, there's still something unsettling about it. The demon star isn't evil. It's not cursed, but it is dying. One of those stars is stealing the other's life. And from Earth, all we see is a gentle dimming, a blink, as if the universe is trying to be polite about murder. Eclipsing binaries aren't rare. We've found thousands of them. Some eclipse every few hours, some every few years. The longest known eclipsing binary, Epsilon Aurigae, has a period of 27.1 years. That means if you saw it eclipse as a child, you'd be middle-aged before you saw it happen again. And the eclipses last almost 2 years. From 2009 to 2011, Epsilon Aurigae dimmed by about 50%. And amateur astronomers all over the world watched, measured, photographed, trying to understand what was blocking the light. We still don't entirely know. The leading theory is that Epsilon Aurigae is orbited by a massive disk of dust and gas, maybe the remnant of a dying star hidden inside. When that disk passes in front of the primary star, we see the eclipse. But we can't see the companion itself. It's hidden, veiled, like something the universe doesn't want us to see clearly yet. And that mystery, that not quite knowing, is part of what makes eclipsing binaries so compelling. Because even when we think we understand, even when the math works out, there's always another layer, another question. Beta Lyrae is another strange one. It eclipses every 12.9 days, but the light curve is unusual. Instead of a sharp dip and recovery, the brightness changes gradually, constantly. There's no stable level. It's always dimming or brightening, just at different rates. Scientists believe this is because Beta Lyrae is so close to its companion that both stars are distorted, stretched, egg-shaped. And as they orbit the amount of surface area, we see changes continuously. Like watching two dancers so close they become one fluid shape, and we're trying to figure out where one ends and the other begins. Some eclipsing binaries are even more extreme. Contact binaries where the two stars are literally touching, sharing an atmosphere. Their outer layers merged into a single envelope while their cores remain separate. These systems are often called over-contact binaries, and they're thought to be the precursors to stellar mergers. In a few million years, those two stars will collapse into one, a single rapidly rotating star. Or maybe if they're massive enough, they'll explode. A supernova triggered not by a single star's death, but by the collision of two. And here's something that might make you pause. Our sun is relatively alone. It has planets, yes, asteroids, comets, but no stellar companion. Most stars aren't that lucky. Recent surveys suggest that more than half of all sun-like stars exist in binary or multiple star systems. They're born together, orbit together, sometimes die together. And that means that out there on planets orbiting those stars, if there are beings looking up at their sky, they don't see one sun. They see two, maybe three. And their days don't end with a single sunset. They end with a dance of light shadows crossing shadows, one star setting, while the other rises, or both, setting together, plunging the world into night. What would that do to a civilization? To a mythology? If your sky had two suns, would you still worship one? Would you imagine they were siblings, lovers, enemies? And if every few days one dimmed because the other passed in front of it, would you see it as a battle, a kiss? Or would you like us eventually realize it's just geometry? Just two massive spheres of fusion, bound by gravity, circling each other in the dark. The beautiful thing about eclipsing binaries is that they teach us something fundamental. Darkness doesn't always mean death. Sometimes it just means something's in the way. And that shadow, that temporary dimming, can tell us everything. The size of the stars, their masses, their temperatures, how far apart they are, how fast they're orbiting, even what they're made of. Because when one star passes in front of another, the light we see is filtered through the outer layers of the foreground star. And hidden in that filtered light are absorption lines, fingerprints of elements, carbon, oxygen, iron, hydrogen, a chemical signature written in shadow. Scientists call this eclipse spectroscopy. And it's one of the most powerful tools we have for studying stars we can't resolve individually. Because even with our best telescopes, even with Hubble or James Webb, most binary stars are too close together to see as separate points of light. They look like one star, but when they eclipse, when one moves in front of the other, the light changes in ways that reveal their secrets. The shape of the eclipse curve tells us the size ratio. The duration tells us the orbital speed. The depth tells us the brightness ratio. It's like solving a puzzle where every piece is a wavelength of light. And sometimes in rare systems, we see both stars eclipse. First, the brighter star passes in front of the dimmer one and we see a deep primary eclipse. Then, half an orbit later, the dimmer star passes in front and we see a shallower secondary eclipse. And by comparing those two eclipses, we can build a complete picture of the system. Two stars we've never seen separately. Two stars whose light blends together into one point in our telescopes. And yet, we know their sizes, masses, temperatures, ages. We know their story just by watching them pass in front of each other. It's humbling in a way, to realize how much information is hidden in something as simple as a shadow. To realize that what ancient people feared, what they called demons and ghouls and omens of death, was actually one of the universe's gentlest gifts. A way of showing us that even when things go dark, even when the light dims, it's not the end. It's just a pause, a moment of occultation, and the light always comes back. Have you ever stood between someone and a light source, felt your shadow stretch out long and thin? That's all an eclipse is. On a cosmic scale, yes. Across distances measured in millions of miles. But fundamentally, it's the same. One object blocking light from another. And the fact that we can see that happen, that we can measure it, that we can use it to understand stars we'll never visit, is one of those quiet miracles that's easy to take for granted. Because here's the thing. Most of what we know about stars, we learn by watching them from a distance. We can't touch them, can't sample them, can't send probes into their cores. All we have is their light. And in that light filtered through atmospheres and interstellar dust, bent by gravity and redshifted by expansion, we've learned to read entire biographies. Birth life, death, chemistry, motion, fate. All from light, all from watching. And eclipsing binaries remind us that sometimes the best way to see something clearly is to watch it disappear, to watch it dim, to wait for the shadow to pass and see what remains. Because in that brief darkness in that moment, when the light is blocked, we learn more than we ever could from steady brightness. But not all variable stars are so predictable. Not all rhythms are so clean. Some stars don't pulse steadily. Some don't eclipse gracefully. Some are young, unstable, still figuring out how to burn. And when they change, they don't breathe. They flare. They erupt. They throw tantrums of light and heat that can be seen across entire star-forming regions. Youth even in stars comes with fire and uncertainty. Imagine being barely 1,000,000 years old, still wrapped in the cloud of gas and dust you were born from. Still figuring out how to balance the crushing weight of your own gravity against the nuclear fire trying to tear you apart. You're not stable yet, not calm, and sometimes, without warning, you flare. Your brightness surges 100 times, 1,000 times, flooding the surrounding nebula with light so intense it can trigger the birth of other stars, or destroy the planets trying to form around you. This is what young stars do. They don't ease into existence, they erupt into it. We call them eruptive variables. And unlike the steady pulse of Cepheids or the predictable eclipses of binary systems, these stars are chaotic, unpredictable, volatile. They're the toddlers of the cosmos, full of energy they don't know how to control yet. And when we watch them, we're watching something raw, something that hasn't learned to behave, something still becoming. The most famous of these young rebels are called T-Tauri stars, named after the first one discovered in the constellation Taurus. T-Tauri itself was identified in 1852 by John Russell Hind, a British astronomer who noticed it was unusually variable. Some nights it shone at 10th magnitude, other nights it dimmed to 14th. That's a brightness change of about 40 times. And it happened irregularly, no pattern, no rhythm, just chaos. For over a century, astronomers didn't understand what they were looking at. T-Tauri seemed to defy everything they knew about stars. It was cooler than the sun, redder, but far more luminous. It flickered constantly. Its spectrum showed strange emission lines, signs of hot gas moving at high speeds. And surrounding it was a faint nebula, glowing softly as if the star was still embedded in the material it formed from. Which, as it turns out, it was. T-Tauri stars are pre-main sequence stars. They're less than 10 million years old, still contracting under their own gravity, not yet hot enough in their cores to fuse hydrogen steadily. They're almost stars, not quite. And because they're still collapsing, still accreting material from the protoplanetary disk around them, their brightness fluctuates wildly. Sometimes the accretion rate increases. Material from the disk spirals inward, crashes onto the star, releases gravitational energy, and the whole system brightens. Other times, the disk becomes unstable fragments or develops clumps and the light dims. There's no equilibrium yet, just turbulence. And that turbulence has consequences. T-Tauri stars produce powerful stellar winds, jets of material shooting out from their poles at hundreds of kilometers per second. These winds can clear away the surrounding gas and dust carving cavities in the nebula. In some cases, the winds are so strong they disrupt the protoplanetary disk, entirely preventing planets from forming. In other cases, they compress material elsewhere, triggering the birth of new stars. It's a paradox. The chaos of youth both creates and destroys. Scientists estimate there are millions of T-Tauri stars in our galaxy alone. Most are hidden embedded in dense clouds where visible light can't penetrate. But with infrared telescopes, we can see through the dust. And what we see is beautiful and violent. Stars wrapped in glowing cocoons. Disks swirling with material that will someday become planets. Jets carving through the interstellar medium like cosmic blowtorches. And through it all, the stars themselves flickering, flaring, trying to stabilize. But some young stars don't just flicker. Some explode into brilliance so sudden, so extreme, that for a few months they become the brightest objects in their entire star-forming region. These are called Fu Orionis events, named after the star Fu Orionis, which in 1936 did something extraordinary. Before 1936, Fu Orionis was invisible to the naked eye. It sat at about 16th magnitude, far too faint to see without a telescope. And then over the course of just a few months, it brightened by a factor of 250. It went from magnitude 16 to magnitude 9, suddenly visible, suddenly blazing. And it didn't just flare and fade, it stayed bright for years, decades. Even now, almost 90 years later, Fu Orionis is still brighter than it was before the outburst, still glowing at the elevated level it reached in 1936. No one saw it coming, no one predicted it. And for years afterward, astronomers debated whether it was a unique event or part of a broader phenomenon. The answer came in 1969 when another star, V Cynos 57 Cygni, did the same thing. And then again in 1970, and a handful of times since. We've now identified about 10 confirmed Fu Orionis events in recorded history. 10 stars that suddenly, without warning, increased in brightness by factors of 100 or more and stayed bright for decades. The current theory is that FU Orionis outbursts are caused by dramatic increases in the rate at which material from the protoplanetary disk falls onto the star. Something may be a gravitational instability, maybe an interaction with a companion star, causes the disk to dump huge amounts of material onto the central star all at once. That material crashes into the star at velocities of hundreds of kilometers per second, converting gravitational potential energy into heat and light. The star's surface temperature skyrockets, its luminosity surges, and for years, sometimes centuries, the accretion continues at this elevated rate before finally settling back down. But here's the unsettling part. We don't know what triggers these events. We don't know if they're random or cyclical. We don't know if every young star goes through an FU Orionis phase, or if only certain types do. And we don't know what effect these outbursts have on planetary formation. If a star suddenly dumps 100 times more energy into its protoplanetary disk, does that destroy any planets trying to form? Does it vaporize the inner disk? Or does it paradoxically help planets form by compressing and heating material in the outer regions? One study in 2016 suggested that FU Orionis outbursts might be common, happening once every 10,000 years for a typical young star. If that's true, and if the outburst lasts 100 years, then at any given time, about 1% of all young stars should be in an FU Orionis state. But we've only found 10, which means either the outbursts are much rarer than we think, or much shorter, or we're not looking in the right places, or all three. There's another class of eruptive variables slightly different called XORs, named after the prototype EX Lupi. These stars also flare unpredictably, but their outbursts are shorter, weeks or months instead of years, and they can repeat. EX Lupi itself erupted in 1950s again in 2008, and possibly other times we didn't catch. During the 2008 outburst, its brightness increased by about 100 times, over a few weeks peaked, and then slowly faded back to normal over a few months. Astronomers watch carefully using everything from ground-based telescopes to the Spitzer Space Telescope, and they saw something remarkable. During the outburst, the inner disk became so hot it started to evaporate. Water methane and other volatile molecules turned to gas and were driven away by radiation pressure. The chemistry of the disk changed. Crystalline silicates formed minerals that require high temperatures to condense. And when the outburst ended, when the star dimmed back to normal, the disk began to cool and settle again. But it wasn't the same as before. The outburst had altered it, baked it, left scars. So, if you're a planet trying to form around an XOR or an FU Orionis star, your environment is unstable. One decade, you're gently accumulating dust and ice building up your mass. The next decade, your star erupts, floods you with radiation, evaporates your volatiles, maybe even disrupts your orbit. And then it calms down again, and you have to start over. It's no wonder that studying planetary formation around young eruptive stars is so challenging. The conditions keep changing. The rulebook keeps getting rewritten. There's also evidence that these outbursts can trigger additional star formation in the surrounding cloud. When a young star flares, it sends out shock waves that compress nearby gas. And if that gas is dense enough, if conditions are right, the compression can trigger collapse. New stars begin to form, which means that star formation isn't always a smooth, gradual process. Sometimes it happens in bursts. One star erupts, the shock wave spreads, and a cascade of new births begins. Think about that for a moment. The chaos of one star's youth can trigger the birth of dozens, maybe hundreds of others. It's like a cosmic chain reaction. And it means that the stars in a given region aren't necessarily the same age. Some are older, more settled. Others are younger, still forming, triggered by the tantrums of their predecessors. The galaxy doesn't grow old uniformly. It ages in patches, in waves, in bursts of fire and silence. And this raises a question. What was our sun like when it was young? Did it go through an FU Orionis phase? Did it erupt and flare and flood the early solar system with radiation? We don't know. We can't look back. But if it did, that would have profound implications for how the planets formed, for how Earth got its water, for why the inner planets are rocky and the outer planets are gas giants. Maybe the early sun's violence drove volatiles outward, leaving the inner system dry and hot. Or maybe the outbursts helped compressing material in the outer disk, allowing Jupiter and Saturn to grow quickly before the gas dispersed. Scientists study T Tauri stars and FU Orionis events not just to understand them, but to understand us, to see what we came from. Because every star goes through this phase. Every star is born in chaos. And the fact that we exist, that Earth exists, that stable life-bearing planets exist, means that somehow, despite the violence, despite the unpredictability, things can settle. Order can emerge from disorder. Calm can follow storm. But that takes time, millions of years. And most young stars don't make it that far with their disks intact. The stellar winds are too strong, the outbursts too frequent. The material disperses before planets can fully form. So, when we look at systems like ours, where multiple planets survived, where rocky worlds and gas giants coexist in relatively stable orbits, we're looking at a kind of cosmic luck, a series of events that could have gone wrong but didn't. And part of that luck is timing. If the sun's FU Orionis phase happened too early, the planets wouldn't have started forming yet. If it happened too late, they might have been destroyed. But it happened if it happened at all at just the right moment to allow what came next. And here's something strange. When we look at young stars today, when we watch them flare and dim and throw tantrums, we're seeing our own past. Light from T Tauri stars takes hundreds or thousands of years to reach us, yes. But the stars themselves are at a stage our sun passed through 4.6 billion years ago. They're showing us what we were, and in a way they're showing us what we survived. Because if those outbursts can destroy planets, they can also forge them. The same heat that evaporates ice can crystallize minerals. The same winds that strip atmospheres can compress gas into dense cores. Creation and destruction happening simultaneously, inseparably. Have you ever watched a child learn to walk? They fall. A lot. They stumble. They crash into things. And every time you wonder if they'll give up, but they don't. They keep trying. And eventually they find their balance. That's what young stars are doing. Learning to stand, learning to burn steadily. And the flares, the outbursts, the chaos, those aren't failures. Those are attempts, practice, the universe figuring itself out. In a few million years, most T Tauri stars will calm down. They'll settle onto the main sequence, start fusing hydrogen in their cores at a steady rate, and shine calmly for billions of years. The tantrums will end, the disks will disperse or form planets, and what's left will be a stable system. Orderly, predictable, until eventually old age brings its own kind of chaos. But that's later. That's much later. For now, these young stars are loud, bright, unpredictable, and they remind us that stability is earned, that calm is something the universe has to learn, and that sometimes the brightest moments come not from balance, but from its absence. Still, eruptive variables are only one flavor of stellar chaos. There are other stars, older stars, that also change brightness dramatically. But these aren't young and figuring things out. These are ancient, dying. And their brightness changes not because they're learning to burn, but because they're learning to steal. A slow theft, silent until the moment it explodes. Imagine a star so dense, so compressed, that a teaspoon of its material would weigh as much as a car. It's the remnant of a sun that died collapsed, and now sits quietly in the dark, no longer burning, just cooling. But it's not alone. Orbiting close, sometimes so close they're almost touching, is a companion star. Still alive, still burning. And slowly, Atom by atom, the dead star pulls material away. Hydrogen streams from the living star to the dead one, spiraling down onto its surface. And there it waits, accumulates, compresses, heats, until one night, without warning, the stolen hydrogen ignites, and the dead star blazes back to life in an explosion so bright it can be seen halfway across the galaxy. This is a nova, not a new star despite the name, but a star reborn, briefly, violently. And the systems that produce them are some of the strangest, most unforgiving partnerships in the cosmos. We call them cataclysmic variables. And unlike the young, chaotic, eruptive stars we just explored, these are old, ancient even. Stars at the end of their lives locked in a fatal embrace. One stealing, one losing. Both trapped by gravity in a dance that can only end in destruction. The centerpiece of every cataclysmic variable is a white dwarf, a stellar corpse. When a star like our sun runs out of hydrogen fuel, it swells into a red giant, sheds its outer layers, and what's left behind is the core. About the size of Earth, but with the mass of the sun. No fusion happening anymore, no energy generation, just the quantum pressure of electrons keeping the star from collapsing further. It's stable, inert. It can sit there for trillions of years, slowly cooling, fading into darkness. But if there's a companion nearby, if another star orbits close enough, the white dwarf's gravity can reach out and pull material away. And that changes everything. Material doesn't fall straight onto the white dwarf. It has angular momentum. It spirals, and as it spirals, it forms an accretion disk, a flat ring of gas orbiting the white dwarf at tremendous speeds. Friction within the disk heats the gas to tens of thousands of degrees, hot enough to glow, sometimes hot enough to emit X-rays. The disk can be so bright it outshines both stars. And from Earth watching through a telescope, what we see is a binary system with a strange flickering glow, rapid changes in brightness, irregular pulses, signs of chaos. But the disk is just the prelude. The real drama happens on the surface of the white dwarf. As material from the disk slowly drifts inward, it settles onto the white dwarf's surface. Hydrogen mostly, pure unburned fuel. And because the white dwarf's gravity is so strong that hydrogen is compressed immediately, squeezed, heated, but not enough to ignite, not yet. It just sits there, building up, layer after layer, year after year, until the pressure and temperature at the base of the accumulated layer reach a critical threshold, and then it ignites, all at once, a thermonuclear runaway. The entire surface of the white dwarf erupts in fusion. And for a few days, sometimes a few weeks, the system becomes a nova. The first recorded nova was in 1572, Tycho's supernova, the one we mentioned earlier. But that wasn't a nova. That was a supernova, a much more energetic event. True novae, the smaller repeating explosions we're talking about, now started being recognized in the late 1800s as astronomers began systematically photographing the sky and noticing stars that appeared where none had been before. They called them novae Latin for new stars because they seemed to appear out of nothing. But by the early 1900s, spectroscopic studies revealed the truth. These weren't new stars. They were old stars flaring back to life. And they weren't rare. They were everywhere. A typical nova increases in brightness by a factor of 50,000 to 100,000. That's 10 to 11 magnitudes. A star invisible to the naked eye can suddenly become one of the brightest objects in the night sky. And then, just as quickly, it fades. Within days, the brightness drops. Within weeks, it returns to something close to its pre-outburst level. And the system goes quiet again. The white dwarf resumes accreting material. The companion star continues losing mass, and the cycle begins again. Some novae only erupt once in recorded history. We call them classical novae, The most famous is probably Nova Aquilae 1918, which appeared in June of that year and became the brightest nova of the 20th century. At its peak, it reached magnitude -1.4, brighter than Sirius, brighter than any star in the sky except the sun. It was visible during the day for several days. People noticed it. Newspapers wrote about it. And then it faded. By the end of the year, it was gone invisible to the naked eye, back to its quiet existence as a faint binary system no one looks at anymore. But other novae erupt repeatedly. We call them recurrent novae, and they're fascinating because they give us a chance to watch the same system explode multiple times, to compare outbursts, to study how the white dwarf changes, to understand the mechanics of these thermonuclear runaways in detail. The most famous recurrent nova is RS Ophiuchi. It sits about 5,000 light-years away in the constellation Ophiuchus. And since we started keeping detailed records, it has erupted 7 times, in 1898, in 1933, in 1958, in 1967, in 1985, in 2006, and most recently in 2021. Each eruption follows the same pattern. The star brightens from magnitude 12 to magnitude 4 or 5 in a matter of hours. It stays bright for a few days, sometimes a few weeks, and then it fades back to obscurity. The interval between eruptions isn't regular. Sometimes it's 15 years, sometimes 20, sometimes 30. But it always happens, like clockwork if the clock is broken. Why does RS Ophiuchi erupt so frequently compared to other novae? The answer lies in the accretion rate. The companion star in the RS Ophiuchi system is a red giant much larger and more luminous than the Sun. It's shedding material rapidly, and the white dwarf is close enough, massive enough to pull in huge amounts of hydrogen. That means the critical threshold, the point where the accumulated layer ignites, is reached much faster. Instead of waiting thousands or tens of thousands of years between eruptions, RS Ophiuchi only needs a couple of decades. It's a fast-burning system, a stellar vampire feeding voraciously. During the 2006 outburst, astronomers used every available telescope to watch: optical, infrared, X-ray, gamma ray. They tracked the evolution of the explosion in real time, and they saw something remarkable. The ejected material, the hydrogen that erupted off the white dwarf's surface, didn't just dissipate into space. It collided with material the red giant had shed earlier, and that collision created a shock wave, a ring of hot glowing gas expanding outward at thousands of kilometers per second. The ring was visible in X-rays, a perfect circle growing fading, carrying the energy of the explosion out into the interstellar medium. And here's what makes it unsettling. Every time RS Ophiuchi erupts, the white dwarf ejects some of the material it accreted, but not all of it. Some remains. Some adds to the white dwarf's mass. And if the white dwarf keeps gaining mass, if it keeps stealing material from its companion, eventually it will reach a critical limit, about 1.4 solar masses, the Chandrasekhar limit. And at that point, the electron pressure holding the white dwarf up won't be enough anymore. The star will collapse, rebound, and detonate in a Type Ia supernova, a true supernova, one that will destroy both stars, outshine the entire galaxy for weeks, and be visible from billions of light years away. We don't know if RS Ophiuchi is heading toward that fate. It might be. Or it might eject more mass than it keeps staying below the limit forever. But the possibility is there. Every eruption is a step. And somewhere in some galaxy at this very moment, a recurrent nova is ticking closer to its final explosion. And when it happens, it will tell us something. Because Type Ia supernovae are standard candles. We use them to measure cosmic distances, to map the expansion of the universe, to discover dark energy. And all of that started with systems like RS Ophiuchi, stellar vampires, quiet, patient, deadly. But not all cataclysmic variables erupt on decade-long timescales. Some erupt far more frequently. We call them dwarf novae, and their outbursts are smaller, less energetic, but more common. Instead of waiting years, they flare every few weeks or months. And the mechanism is different. It's not a thermonuclear explosion on the white dwarf's surface. It's an instability in the accretion disk itself. The prototype is Eugeminorum, discovered in 1855. It sits about 250 light-years away, relatively close by cosmic standards. Most of the time, it's around magnitude 14, far too faint to see without a telescope. But every few months, sometimes every few weeks, it brightens to magnitude 8 or 9. That's a change of a factor of about 40. Not as dramatic as a classical nova, but frequent, predictable in a chaotic sort of way. What's happening is this. The accretion disk around the white dwarf is unstable. Most of the time, the disk is cool, dim, and the material flows slowly inward. But under certain conditions, the disk heats up. The viscosity increases, and suddenly the material flows inward much faster, crashing onto the white dwarf at a much higher rate. That rapid accretion releases gravitational energy. The whole system brightens, and for a few days Eugeminorum flares. Then the disk cools, the flow slows, and the system dims again. This cycle repeats over and over, sometimes regularly, sometimes irregularly, depending on the disk's structure and the accretion rate from the companion. Dwarf novae are common. We've found hundreds of them in our galaxy. And they're incredibly useful for studying accretion physics, the process by which material falls onto compact objects. Because we can watch them change in real time, we can see the disk heat and cool, we can measure the outburst timescales, we can compare systems with different orbital periods, different companion stars, different white dwarf masses. And from all of that, we build a picture of how accretion works, how matter behaves in extreme gravity, how energy is transported in turbulent magnetized disks. It's a laboratory we could never build on Earth, but the universe provides it for free. There's another class of cataclysmic variables, even stranger, called polars. In these systems, the white dwarf has a powerful magnetic field, billions of times stronger than Earth's. So strong that it locks the white dwarf's rotation to the orbital period of the companion. They spin together, face each other, like two dancers locked in an eternal gaze. And the magnetic field is so strong, it disrupts the accretion disk. Material from the companion can't spiral. Instead, it follows the magnetic field lines channeling down to the white dwarf's magnetic poles. And there, it crashes into the surface at a significant fraction of the speed of light. The impact heats the gas to millions of degrees, hot enough to emit X-rays. And because the white dwarf is rotating because the poles sweep past our line of sight like a lighthouse, we see the X-rays pulse. On, off, a cosmic heartbeat driven by magnetism and gravity. Polars are rare. We've only found a few dozen. But they're important because they show us what happens when magnetic fields dominate. In most cataclysmic variables, gravity and angular momentum control the flow. But in polars, magnetism wins. It dictates where material goes, how it falls, where it lands. And the result is a system that looks nothing like a typical binary. No disk, no spiral, just streams of plasma following invisible magnetic highways from one star to another. And here's a thought that might make you pause. These systems, these cataclysmic variables, they're not just curiosities. They're the future. In about 5 billion years, our sun will swell into a red giant. It will engulf Mercury, probably Venus, maybe Earth, and then it will shed its outer layers, leaving behind a white dwarf. If somehow any planets survive, if anything remains in orbit, the white dwarf will sit there quietly, cooling, fading. But if another star happens to wander too close, if a binary system forms, then our sun's corpse could become an accretor, a thief, a nova waiting to happen. The same gentle light that warmed Earth for billions of years could in some distant future explode in a thermonuclear fireball. It's unsettling, but it's also strangely beautiful, because even in death, even as a cold, dense remnant, stars can shine again. Have you ever felt stuck, trapped in a situation where you're giving more than you're getting, where something or someone is slowly draining you. That's what the companion stars and cataclysmic variables are experiencing. They're losing mass, losing energy, being pulled apart atom by atom, and they can't escape. Gravity holds them, and over millions of years they shrink, dim, until there's nothing left but the white dwarf, now slightly more massive, and a thin ring of gas where the companion used to be. It's a slow death, a quiet ending. But before it ends, before the companion is completely consumed, the system burns bright, over and over, in flares and eruptions, in theft and explosion. Proof that even dying stars have light left to give. And that brings us to another kind of variability. Not young stars figuring things out. Not dead stars stealing life. But old stars, ancient stars breathing their last. Stars so large, so cool, so unstable, that they pulse like dying hearts swelling and shrinking over months or years, shedding their outer layers into space, preparing for the end. Breath slowing, growing fainter but still breathing. Imagine living for billions of years. You've burned through most of your fuel. Your core is shrinking, collapsing under its own weight. Your outer layers are swelling, cooling, turning red. You're hundreds of times larger than you were in your youth, but thousands of times dimmer per unit of surface area. And you're unstable. Your atmosphere pulses, rises and falls. Sometimes you're bright enough to see across interstellar space. Sometimes you fade into invisibility. And with each pulse, you shed a little more of yourself into the void. Dust, gas. The material that will someday become other stars, other planets, maybe other lives. This is what it means to be old, not in human terms, but in cosmic ones. And the stars that show us this, that breathe this slow, irregular rhythm, are called Mira variables. The name comes from one star, Omicron Ceti. But for centuries, people called it Mira, the wonderful. And it earned that name because it does something almost no other naked-eye star does. It appears, shines brightly for a few months, and then vanishes completely, dropping below naked-eye visibility. And then, almost a year later, it comes back. The ancients didn't know what to make of it. A star that blinks in and out of existence. A star that breathes. It seemed magical, impossible. And for a long time, it was dismissed as observational error. Maybe atmospheric distortion, maybe tired eyes. But in 1596, a Dutch minister and amateur astronomer named David Fabricius was watching the constellation Cetus the Whale, and he noticed something unusual. There was a third magnitude star where no third magnitude star should be. He checked his charts. Nothing. He watched it over the following weeks. It brightened slightly. Then slowly it began to dim. By October, it was fourth magnitude. By November 5th. And by December, it was gone. Invisible. Fabricius assumed it had died, that he'd witnessed the death of a star, and he moved on. But years later in 1609, he saw it again. Same location, same brightness. And this time he watched more carefully. He tracked it for months, saw it brighten, peak, and fade again. And he realized this star wasn't dying. It was pulsing, appearing and disappearing in a cycle. He'd discovered the first known variable star of its kind. We know now that Mira is a red giant about 300 light-years away. It's in the late stages of its life. Its core has stopped fusing hydrogen. It's burning helium in a shell around the core, and that shell is unstable. The energy output fluctuates. Sometimes the outer layers absorb that energy and expand. The star swells, cools, dims. Other times the layers contract, heat up, and brighten. The cycle takes about 332 days, not quite a year. And the brightness change is extreme. At its brightest, Mira reaches second magnitude, easily visible to the naked eye. At its dimmest, it drops to 10th magnitude, requiring a telescope to see. That's a factor of about 1/500 in brightness. one of the largest amplitude variations of any star in the sky. And Mira isn't alone. We've found thousands of stars that behave the same way. Long period variables with cycles ranging from a few months to several years. Brightness changes of factors of 101,000, even 10,000. These stars are all red giants or supergiants. Cool, massive, unstable. And they're all dying, slowly, beautifully, shedding their outer layers in stellar winds so dense you could almost see them if you were close enough. In 2007, astronomers using the Galaxy Evolution Explorer Space Telescope discovered something remarkable about Mira. It has a tail, a comet-like tail of gas stretching 13 light-years behind it. That's longer than the distance from the Sun to the nearest star. The tail is made of material Mira has shed over thousands of years. As Mira moves through space orbiting the center of the Milky Way at about 130 kilometers per second, its stellar wind collides with the interstellar medium. The wind is compressed heated and forms a bow shock, and trailing behind like a cosmic streamer is the material Mira has lost. Hydrogen, helium, carbon, oxygen, dust grains. The building blocks of planets and life drifting slowly through space, waiting to be recycled into something new. Scientists estimate that Mira is losing about 1 solar mass every 10,000 years. That might not sound like much, but over millions of years it adds up. Mira has already shed a significant fraction of its original mass, and what's left is a dense core surrounded by an ever-thinning envelope. Eventually, maybe in another million years, the envelope will be gone entirely, blown away, and what remains will be a white dwarf, a hot, dense ember, slowly cooling in the dark. But for now, Mira is still here, still pulsing, still breathing. The physics behind Mira's variability is complex. Unlike Cepheids, which pulse due to the Kappa mechanism, Mira variables pulse due to a combination of factors. Convection in the outer layers, ionization zones that trap and release radiation, shock waves propagating through the atmosphere, and all of it happening in a star that's already unstable, already near the end of its fuel supply. The result is a pulse that's not perfectly regular. Mira's period 332 days is an average. Sometimes the cycle is a bit shorter, sometimes longer, and the peak brightness varies too. Some cycles Mira reaches magnitude 2, other cycles only magnitude 3 or 4. It's unpredictable, irregular, like the heartbeat of someone very old, very tired, but still holding on. And here's something that makes you think. Mira variables are what our sun will become. Not exactly because the sun is slightly less massive and its evolution will be a bit different. But in broad strokes, yes. In about 5 billion years, the sun will exhaust its core hydrogen. It will swell into a red giant. Its outer layers will reach Earth's orbit, maybe beyond. And it will become unstable. It will pulse. Not as dramatically as Mira, but it will vary. And over a few 100 million years, it will shed those outer layers entirely, creating a planetary nebula, a glowing shell of gas expanding into space. And at the center, a white dwarf, the sun's core. All that will remain. So when you look at Mira, when you watch it brighten and fade, you're looking at the sun's future. You're seeing what happens when a star runs out of time. And it's not violent, not sudden. It's slow, gradual, almost gentle. The star doesn't explode. It just exhales, slowly, over and over, until there's nothing left to exhale. Mira variables are incredibly important for understanding stellar evolution, because they're at a stage most stars will pass through. They're common. Everywhere we look in the galaxy, we find them. Old stars, red stars, pulsing stars. And by studying them, we learn how stars lose mass, how they enrich the interstellar medium with heavy elements, how they prepare for their final transformation into white dwarfs. It's a window into the end of life, not as dramatic as a supernova, but just as important. There's a subclass of Mira variables called semi-regular variables. These stars pulse too, but their periods are less predictable. Sometimes the cycle is a few months, sometimes a year. Sometimes the brightness changes are large, sometimes small. And sometimes, for reasons we don't entirely understand, they stop pulsing altogether for a while. They just sit there, steady. And then without warning, the pulsations resume. It's as if the star is struggling to maintain a rhythm, like an old clock that skips, stutters, but keeps ticking. One famous semi-regular variable is Betelgeuse. You've probably heard of it. It's the red supergiant in the constellation Orion, marking the hunter's shoulder. It's one of the brightest stars in the night sky. And it varies, not as dramatically as Mira, but noticeably. Most of the time, Betelgeuse sits around magnitude 0.5, a distinctly reddish star. But every few years, it dims to magnitudes 1.2 or so. And in late 2019, it did something unprecedented. It dimmed much more than usual. By February 2020, it had dropped to magnitude 1.6. That's the faintest it had been in recorded history, and people noticed. Even casual stargazers saw it. Betelgeuse, normally one of the top 10 brightest stars, was suddenly fainter than the stars around it. Speculation ran wild. Was Betelgeuse about to explode? To go supernova? It's a massive star, at least 10 to 20 times the mass of the Sun. It's already in its red supergiant phase, and we know that stars like Betelgeuse don't have long left. Maybe a few 100,000 years, maybe less. In cosmic terms, that's tomorrow. So, when it dimmed, astronomers wondered, could this be it? Could we be about to witness a supernova in real time? But by mid-2020, Betelgeuse began to brighten again. By mid-2021, it was back to normal. The dimming wasn't a precursor to explosion. It was something else. The current theory is that Betelgeuse ejected a large cloud of dust. The dust obscured the star from our view, blocking some of its light. And as the dust dissipated, drifted away, the star's brightness returned. It was an ejection event, a massive stellar wind. Not unusual for a red supergiant, but larger and more sudden than expected. And it reminded us, these stars, these old giants, they are not predictable. They do strange things. They eject material. They pulse irregularly. They surprise us. And one day, maybe soon, maybe not. For thousands of years, Betelgeuse will explode. And when it does, it will be visible during the day, brighter than the full moon, a second sun in the sky for weeks. But that day isn't today. Today, Betelgeuse is just breathing, pulsing, like Mira, like thousands of other red giants scattered across the galaxy. Mira variables teach us patience, because their cycles are long. To study one properly, to understand its period and amplitude, you need years of observations, sometimes decades. And that's work that can't be rushed. Telescopes can help. Automated surveys can track thousands of stars simultaneously. But there's still a role for patient observers, amateurs with backyard telescopes, people who watch the same stars night after night, season after season, year after year, recording, measuring, contributing to databases that professional astronomers use. The American Association of Variable Star Observers, AVSO, has been collecting observations since 1911, over a century of data. Millions of observations, most of them contributed by volunteers, people who love the sky, who watch it change. And when you look at those light curves, those plots of brightness over time, you see something beautiful. You see the rhythm of dying stars, the slow exhalation of giants, and you see consistency. Despite the irregularities, despite the unpredictability, there's a pattern, a shape, a tendency. And that pattern tells a story. Scientists use Mira variables to map the structure of the galaxy. Because these stars are bright, even at their faintest, they're still visible across thousands of light years. And because they pulse, we can sometimes estimate their distances using period luminosity relationships, similar to Cepheids, but less precise. Mira variables aren't standard candles. They're more like approximate candles, but approximate is better than nothing. And when combined with other distance measurements, they help us build a three-dimensional map of where stars are, where old populations concentrate, how the galaxy has aged over time. And here's something that might make you pause. When you see a Mira variable, when you watch it brighten and fade, you're seeing a star in its final act. The curtain is closing, slowly. And with every pulse, a little more of the star leaves the stage. But that material doesn't vanish. It drifts through space, cools, condenses into dust grains. Those dust grains collide, stick together, become part of molecular clouds. And in those clouds, new stars form, new planets, maybe new life. So the death of a Mira variable isn't an ending, it's a transition, a passing of material from one generation to the next. And that's what variable stars teach us over and over. Change is not decay. Variability is not failure. It's transformation. It's the universe recycling itself, taking what was and making what will be, the old becoming the new, the dying becoming the living. And in that cycle, there's a kind of immortality, not the immortality of an individual star, but the immortality of matter, of atoms, of light, continuous, unending, eternal. But sometimes change doesn't follow the patterns we've come to expect. Sometimes stars do things we can't explain, things that don't fit our models, things that make us question what we thought we knew. Mystery is not failure, it's invitation. After centuries of watching stars change, after building models and theories, after learning to read their light like language, you'd think we'd have it figured out. That every dimming, every brightening, every pulse would fit neatly into a category. Cepheid, binary, nova, Mira. But the universe doesn't care about our categories. And every few years, a star does something so strange, so unexpected, that it reminds us how much we still don't understand. How much darkness remains between the points of light. And sometimes those mysteries become more famous than the stars themselves. In 2011, astronomers working with data from NASA's Kepler Space Telescope noticed something odd about a star 470 light-years away. The star had a designation KIC 846852, but no one paid much attention to it. Just another F-type main sequence star, slightly larger and hotter than the Sun, sitting quietly in the constellation Cygnus. But when citizen scientists combing through Kepler data flagged it when professional astronomers took a closer look, they saw something that shouldn't exist. The star's brightness was dipping. Not regularly, not predictably, but in strange asymmetric patterns. Sometimes the light dropped by a few percent, sometimes by 15%. And in one event in 2013, the brightness plummeted by 22%. For several days, 22%. That's massive. For comparison, when Jupiter, the largest planet in our solar system, passes in front of the Sun from a distant observer's perspective, it blocks about 1% of the Sun's light. To block 22%, you'd need something enormous, something much larger than Jupiter, maybe something as large as the star itself. But that doesn't make sense. Planets don't get that big. And if it were a companion star eclipsing the dips, would be regular, predictable. This wasn't. The dips were irregular, chaotic. Different shapes, different depths, different durations. It was as if something massive and strangely shaped kept passing in front of the star. But what the star earned a nickname. Tabby's star, after astronomer Tabitha Boyajian, who led the team studying it. And the hypotheses started piling up. Maybe it was a swarm of comets, a family of icy bodies on eccentric orbits passing in front of the star in unpredictable intervals. That could explain the irregular dips. But comets are small. You need millions of them all clustered together, all moving in coordinated paths. Possible, but unlikely. Maybe it was a debris field, the remnants of a shattered planet or a colliding asteroid. But debris spreads out over time. It doesn't stay clumped, and the dips kept happening. Years later, still irregular, still strange. And then someone suggested something that captured the public's imagination. What if it's not natural? What if it's a megastructure? A Dyson swarm? A massive array of solar panels or habitats built by an advanced civilization, orbiting the star, harvesting its energy. The dips would be the structures passing in front of the star, blocking its light. Different structures, different sizes, different orbits. It would explain the irregularity, the asymmetry, the sheer size of the occultations. And for a few months, Tabby's star became the most talked about star in astronomy, the alien megastructure star. News outlets ran stories, scientists gave interviews. SETI, the search for extraterrestrial intelligence, pointed radio telescopes at it, listening for signals. Nothing. Silence. But the hypothesis, as exciting as it was, didn't hold up to scrutiny, because if the dips were caused by solid structures, opaque objects blocking light, then all wavelengths should dim equally. Visible light, infrared, ultraviolet. But when astronomers looked more carefully, they found the dips were wavelength dependent. Blue light dimmed more than red light. And that means the blocking agent isn't solid, it's particulate, dust. Tiny grains scattering light and scattering blue wavelengths more efficiently than red ones. The same reason Earth's sky is blue, the same reason sunsets are red. So the current leading theory is dust. Clouds of dust orbiting Tabby's star in complex, irregular patterns. Maybe from a family of comets that broke apart. Maybe from a recent collision. Maybe from some other process we haven't thought of yet. The mystery isn't entirely solved. We don't know where the dust came from, why it's arranged the way it is, why the dips are so irregular. But we know it's not aliens. Probably. And that's both disappointing and reassuring. Disappointing because who wouldn't want to find evidence of advanced civilizations? But reassuring because it means we're still learning, still figuring things out. And the universe still has surprises. Tabby's star is just one example. There are others. Stars that defy explanation. Stars that change in ways we can't model. And one of the strangest categories involves stars that don't just dim or brighten. They explode, violently, repeatedly. With energy so extreme, they distort space itself. We call them magnetars. And they're among the most extreme objects in the universe. A magnetar is a type of neutron star, a stellar remnant left behind after a massive star goes supernova. The core collapses, crushing protons and electrons together into neutrons, forming a sphere about 20 kilometers across, but with a mass of 1 to 2 suns. That's a density so extreme that a teaspoon of neutron star material would weigh about 1 billion tons. But magnetars are special. They have magnetic fields, not just strong magnetic fields, the strongest magnetic fields known in the universe, billions of times stronger than any magnet we've ever created on Earth, quadrillions of times stronger than Earth's magnetic field, so strong that the magnetic field itself weighs something, contains energy, warps space. And when a magnetar's magnetic field shifts, when stresses in the crust cause it to snap, and reconfigure the energy released is staggering. In a fraction of a second, a magnetar can emit more energy than the sun produces in 100,000 years. That energy bursts out as gamma rays, X-rays, radio waves. And if you were anywhere nearby, even tens of light years away, that burst could be lethal. Fortunately, the nearest known magnetar is about 9,000 light years away. Far enough that we're safe. Close enough that we can study them. The most famous magnetar event happened on December 27, 2004. A magnetar called SGR 180620, located about 50,000 light years away on the far side of the Milky Way, suffered what's called a starquake. The crust shifted, the magnetic field reconfigured, and in 1/10 of a second it released a burst of gamma rays so powerful it affected Earth's atmosphere. ionized the upper layers, disrupted radio communications, saturated every gamma-ray detector in space. If SGR 180620 had been 10 light-years away instead of 50,000 that burst, might have caused a mass extinction event on Earth, stripped away the ozone layer, irradiated the surface, made the planet uninhabitable for years. But here's what makes magnetars relevant to our story. They're variable stars. Their brightness changes, not in optical light usually, but in X-rays and gamma rays. Soft gamma repeaters, as they're called, flare irregularly. Sometimes weeks pass with nothing, then suddenly a burst, then another, then silence, and we can't predict them. We don't fully understand what triggers the flares. We know it's related to the magnetic field. We know the crust is under immense stress, but the details, the exact mechanisms are still being worked out. And recently, magnetars have been linked to another mystery: fast radio bursts, FRBs. These are brief, intense pulses of radio waves lasting only a few milliseconds coming from distant galaxies. They were first discovered in 2007, and for years no one knew what caused them. Theories range from colliding neutron stars to evaporating black holes to yes, aliens. But in 2020, astronomers detected an FRB coming from within our own galaxy, and the source was a magnetar, SGR 1935 Pluzzy 2154. During a particularly intense flare, it emitted a burst of radio waves strong enough to be detected billions of light years away if it had been aimed at us from another galaxy. Suddenly, at least some FRBs made sense. Magnetars, starquakes, magnetic reconnection events, not aliens. Just the universe being violent. But not all FRBs are explained. Some repeat, some don't. Some come from galaxies where we don't see obvious magnetar candidates. And that means there might be other sources, other mechanisms, or magnetars behave in ways we haven't observed yet. The mystery is shrinking, but it's not solved. Then there's Betelgeuse. We mentioned it earlier how it dimmed dramatically in 2019 and 2020, how everyone wondered if it was about to explode. But let's dig deeper into why that dimming was so strange. Betelgeuse is a semi-regular variable. It pulsates with multiple overlapping periods. One cycle is about 420 days. Another is around 2,200 days. Normally, these cycles combine to produce gentle variations in brightness, a few tenths of a magnitude, nothing dramatic. But in late 2019, Betelgeuse started dimming faster than expected. By January 2020, it was dimmer than it had been in recorded history. And the dimming didn't follow the usual pattern. It was too fast, too deep. Astronomers scrambled. They pointed every available telescope at Betelgeuse, Hubble, ground-based observatories, amateur setups. They took spectra, measured temperatures, analyzed the light, and they found something unexpected. The southern hemisphere of Betelgeuse, the part facing us, was dimmer than the northern hemisphere, significantly dimmer, as if something was blocking the light from that region. And the current theory, supported by observations, is that Betelgeuse ejected a massive cloud of dust. Hot gas from the star's convective layers was thrown outward, cooled, and condensed into dust grains. Those grains absorbed and scattered the star's light, creating a dimming effect visible from Earth. By mid-2020, the dust had dispersed enough that Betelgeuse brightened again. Crisis averted. But the event taught us something important. Even stars we've studied for centuries, stars we thought we understood, can surprise us. Betelgeuse is still going to explode someday. We know that. But when next year? 1,000 years from now? 100,000? We don't know. We can't predict it. All we can do is watch, wait, and hope we're looking when it happens. There's another class of mysteries, stars that vary for reasons we can't even categorize yet. In 2019, astronomers discovered a star HD 139139 that dims every 19 days by about 8%. But the dips are perfectly symmetrical, too symmetrical, and they last Exactly the same amount of time, every cycle. It's like clockwork. But we don't know why. It's not a transiting planet. The dip is too large. It's not an eclipsing binary. The period is too long, and the shape is wrong. It might be a disk, a tilted, warped disk of material orbiting the star, periodically blocking light. But we're not sure. And until we get more data, until we observe it with better instruments, it remains a puzzle. And then there are the stars that brightened or dimmed once in recorded history and never did it again. One-time events that don't fit any known category. Were they novae that we caught at an unusual stage? Were they something else entirely? Without repeated observations, without follow-up, we can't say. They're just data points, anomalies, waiting for someone to connect them to a theory. Have you ever looked at something and realized you were missing the pattern? That the chaos you were seeing was actually order, just on a scale or time scale you hadn't considered? That's what studying variable stars feels like sometimes. We see irregular brightness changes and assume chaos. But maybe there's a rhythm we're not patient enough to detect. A cycle that takes centuries or millennia. Or maybe there really is chaos, randomness, and the universe doesn't owe us patterns. Scientists today have tools previous generations could only dream of. Space telescopes that don't blink, that watch thousands of stars simultaneously for years on end. Spectrographs that can analyze starlight in exquisite detail. Computer models that simulate stellar interiors, atmospheres, magnetic fields. And yet, mysteries remain. Stars like Tabby's star, magnetars we can't predict, Betelgeuse doing things we didn't expect. It's humbling, and it's exciting, because every mystery solved leads to 3 more questions. Every answer opens a new door, and behind every door is another star doing something strange, something wonderful, something we've never seen before. And that brings us to a question worth sitting with. What is the point of all this watching, all this measuring, all these centuries of staring at lights in the sky, recording their brightness, wondering why they change? Is it just curiosity, just the human need to know, or is it something deeper? Because here's the thing, understanding why stars change their brightness isn't just an academic exercise. It's how we map the universe, how we measure distances, how we understand stellar life cycles, element creation, and the structure of galaxies. Every variable star is a piece of data in a much larger puzzle. And when we step back, when we look at all the data together, we see something incredible. We see a universe that's alive, dynamic, constantly changing, not frozen, not static, but breathing, growing, evolving, and we're part of it. The atoms in your body, the calcium in your bones, the iron in your blood, they were made in stars, not stars like the sun. Bigger stars. Stars that live fast, burned bright, and exploded. Supernovae. And the light from those explosions, the variability we study, the brightness changes we catalog, they're echoes of the processes that made us. Made everything. So, when we watch stars change, we're not just observing distant objects. We're studying our origins, our history, where we came from, and maybe if we're lucky, where we're going. But even with all our knowledge, all our tools, all our theories, there are moments when the universe simply says no. When a star does something so bizarre, so inexplicable that all we can do is watch and wonder. And maybe that's okay. Maybe mystery is a gift. A reminder that we're not done yet, that there's still work to do, still light to measure, still stars to watch. And somewhere right now at this very moment, a star is changing, brightening or dimming, pulsing or flaring. And no one's watching it yet, no one knows. But it's happening, waiting to be discovered, waiting to surprise us. And as we turn toward the final part of this journey, as we prepare to let the night settle back into silence, it's worth remembering one more thing, that all these stars, all these changes, all this light traveling across unimaginable distances to reach our eyes, they're part of a single continuous story. The story of how light survives, how it finds us, how it whispers secrets from the past, and how even when it dims, even when it fades, it always finds a way back. Everything that shines changes, and maybe that's why we can't look away. Because deep down, we recognize something in those distant lights, something familiar, not the physics, not the fusion or the gravity or the quantum mechanics, but the rhythm, the pattern, the way things brighten and dim and brighten again, the way nothing stays the same, the way even the most stable-seeming objects have hidden depths, hidden changes, hidden stories. We see ourselves in the stars, not literally, but metaphorically, emotionally. And maybe that's why humans have been watching them for as long as we've had eyes to see. Think about the first person who ever noticed a star change. We don't know who they were. We don't know when it happened. But imagine that moment. You're looking up at the same sky you've seen 1,000 times. And something's different. A star that was bright last season is dim now. Or a star you've never noticed is suddenly visible. And you have no language for it, no framework, no science. Just the observation, the noticing. And maybe for just a moment, you wonder if the sky is alive, if it feels, if it remembers. Because only living things change like that. Only living things pulse and fade and return. Ancient peoples didn't separate the sky from their lives the way we do now. The stars weren't distant objects light years away. They were part of the world, part of the story. When a star brightened unexpectedly, it was an omen. When a star disappeared, it was a warning. The Egyptians tracked Sirius, the brightest star in the night sky, because its heliacal rising, its first appearance at dawn, after a period of invisibility, coincided with the flooding of the Nile. Life-giving floods, predictable, annual, essential. And the star marked the time. Not because the star caused the flood, but because both were part of the same rhythm, the same cycle, earth and sky breathing together. The Polynesians navigated thousands of miles of open ocean using the stars. Not maps, not compasses, just stars. They memorized rising points, setting points, the paths certain stars traced across the sky. And if a star dimmed or moved unexpectedly, it mattered. It changed the navigation. It changed the journey, so they watched carefully, passed the knowledge down through generations. Oral traditions, stories embedded in constellations. And those stories weren't just about navigation. They were about identity, belonging, knowing where you were in the vastness. Because when you're in the middle of the ocean, with no land in sight, the stars are the only thing telling you you're not lost. Even now, in our age of satellites and GPS and light pollution, we still look up. Maybe not as much, maybe not with the same necessity, but we do. And when we see something unexpected, when a meteor streaks across the sky, or a planet aligns, or a star seems brighter than usual, we stop. We point. We tell whoever's nearby, look, did you see that? Because there's something in us, something ancient and persistent that wants to witness, that wants to be part of the sky's story, even if we don't understand it, even if we'll never travel there. We watch. And variable stars are perfect for this, because they change on human timescales, not geological timescales, not evolutionary timescales, but timescales we can observe. A Cepheid pulses every few days. Algol eclipses every 3 days. Mira brightens and fades over the course of a year. You can watch these changes with your own eyes in your own lifetime. You don't need a telescope. You don't need a PhD. You just need patience and a clear sky and the willingness to look at the same spot night after night and notice the difference. Amateur astronomers have contributed enormously to the study of variable stars, more than almost any other field of astronomy, because variable star observation doesn't require expensive equipment, a pair of binoculars, a notebook, an eye for detail, and time. Lots of time. Professional astronomers can't watch every variable star every night. They have other projects, other priorities. But amateurs can. And they do. The American Association of Variable Star Observers, which we mentioned earlier, has over 1 million observations submitted by volunteers, people from every continent, every walk of life, watching, recording, contributing. And sometimes amateurs make discoveries professionals miss. In 2008, a Finnish amateur astronomer named Arto Oksanen was observing a T Tauri star called X Lupi when it began to brighten unexpectedly. He reported it. Professional telescopes swung into action. And for months, scientists watched as EX Lupi underwent one of its rare outbursts, gaining insights into how young stars accrete material, how disks become unstable, how planets might form in chaotic environments. All because someone was watching, someone noticed. There's a kind of intimacy in that, in spending years observing the same star, learning its moods, its cycles, knowing when it should be bright, when it should be dim, and noticing when it breaks the pattern. It's not so different from knowing a person, watching them over time, noticing when something's off, when they're quieter than usual, brighter than usual, changed. And in that noticing, there's a relationship, not a human one, but a relationship nonetheless, between observer and observed, between the watcher and the watched. Scientists talk about this sometimes, though not always in those terms. They talk about favorite stars, systems they've studied for decades, light curves they know by heart. And there's affection in their voices, not anthropomorphism, not sentimentality, but genuine connection. Because when you spend enough time with something, when you invest years trying to understand it, it becomes part of your life, part of your story. And when it does something unexpected, when it surprises you, there's a thrill, not just intellectual, emotional, like seeing an old friend after a long absence and realizing they've changed, grown, become someone slightly different. And here's something worth considering. Variable stars teach us that stability is rare, that constancy is the exception, not the rule. We look at the sun and think this is normal. This is how stars behave, steady, reliable, day after day, year after year, the same warm light. But the sun is unusual in its steadiness. Most stars vary, pulse, eclipse, flare, dim. And the fact that the sun doesn't, the fact that it's been stable for billions of years, stable enough for life to evolve, for civilizations to rise, for us to exist, that's not guaranteed. That's luck. Or maybe it's selection bias. Maybe life can only arise around stable stars. And so we find ourselves here looking out at a universe full of variability and thinking we're the norm, when really we're the outliers. But variability isn't bad, isn't dangerous. Well, sometimes it is. If the sun suddenly became a Cepheid, if it started pulsing, Earth would freeze and roast in alternating cycles. Life would end. But in a broader sense, variability is what makes the universe interesting. It's what allows change, evolution, new structures, new elements, new possibilities. If stars never changed, if they just burned steadily from birth to death, the universe would be static, boring, predictable. But stars do change. They pulse and explode and steal and shed. And in doing so, they create, they destroy, they transform. And that dynamism, that constant flux, is the engine of everything. Galaxies, planets, life, us. There's also a kind of comfort in variable stars, a reminder that change is natural, that brightness and darkness are both temporary, that things cycle, return, that even when something dims, even when it seems to disappear, it can come back. Mira fades into invisibility every year, and every year it returns. RS Ophiuchi erupts, shines brilliantly, and then goes quiet. But it always erupts again. The rhythms might be long, longer than a human lifetime, but they're there, persistent, patient, eternal. And maybe that's what we're really looking for when we watch the stars. Not just knowledge, not just data, but perspective, a sense of scale, a reminder that our problems, our worries, our daily struggles, they're happening on a stage so vast, so ancient, that the light reaching our eyes left its source before we were born, before our grandparents were born, before humans existed. And it will continue long after we're gone. The stars will still be there, still pulsing, still changing, still shining. And there's something grounding in that, something that makes the chaos of human life feel manageable, survivable. Because if stars can endure millions of years of change, if they can pulse and dim and brighten and still hold together, maybe we can too. Have you ever had a night where you couldn't sleep, where your mind was racing and nothing helped? And you went outside, looked up and saw the stars, and for just a moment, the noise quieted, the anxiety dimmed, because you remembered you're part of something larger, something that doesn't care about deadlines or bills or arguments or mistakes. The stars are indifferent to our struggles, but in that indifference, there's a strange kind of peace, because it means our struggles aren't the center of the universe. They're just ours, small, temporary, survivable. Variable stars in particular seem to understand this. They show us that change is constant, that nothing lasts, but also that nothing is truly lost. Mira sheds its outer layers. Those layers drift into space, cool, condense, become dust. And that dust becomes part of a molecular cloud. And that cloud collapses into new stars, new planets. The cycle continues, unbroken. So when Mira fades, it's not dying in the permanent sense. It's transforming, becoming something else. And maybe that's how we should think about our own changes, our own losses, not as endings, but as transformations, becomings. Scientists often say that astronomy is humbling, and it is. When you realize how small Earth is, how brief human history is, how insignificant we are in the grand scheme. But it's also empowering because we're here, we're conscious. We can look up, understand what we're seeing, and feel connected to it. We're made of star stuff, as Carl Sagan famously said. The atoms in our bodies were forged in the cores of massive stars, the calcium in our bones, the iron in our blood, the oxygen we breathe, all of it created in stellar furnaces expelled in supernovae drifting through space for billions of years before coalescing into a planet where life could begin. We are literally the universe looking at itself, stars observing stars, light studying light. And when a star changes brightness, when it pulses or dims or flares, it's not separate from us. It's part of the same story, the same process, the same cosmic dance. We watch because we're curious, yes, but also because on some level we recognize the pattern, the rhythm of birth, life, death, and rebirth, the cycle of light and darkness, the inevitability of change. And in recognizing it, we feel less alone. Because if even stars, those vast nuclear furnaces burning across unimaginable distances, if even they experience change, transition, uncertainty, then maybe change isn't something to fear. Maybe it's just part of existing, part of being, part of the universe doing what it does. And that brings us to the final thought, the final breath of this long, quiet journey through the stars. We've traveled from ancient observers noticing omens, to young astronomers solving mysteries, to modern scientists cataloging thousands of variable stars and still finding new ones. We've seen stars pulse like hearts eclipse, like dancers erupt, like children steal like vampires and fade like elders. We've seen chaos and order, predictability and surprise light and shadow. And through it all, one truth has emerged. Clear, simple, undeniable. That variability isn't the exception, it's the rule. And that's not something to mourn, it's something to celebrate. Because in a universe where everything changes, where nothing lasts forever, light still finds a way, still reaches us, still tells its story. And we, against all odds, are here to listen. We've walked through ancient eyes and modern mysteries, through light and silence, through stars that pulse like hearts and stars that dim like memories. We've met deaf astronomers who heard what others couldn't, women computers who measured the universe from wooden desks, and amateur observers who watched the same patch of sky for decades, waiting for a single moment of change. And through it all, we've been asking one question, quietly, persistently, the way stars ask their own questions across the void. Why do some stars change their brightness? And maybe we found something better than an answer. We've found a story. Because here's what we've learned. Stars change for 1,000 different reasons. Some pulse because their outer layers trap and release energy in endless cycles, swelling and shrinking like cosmic lungs. Cepheids, RR Lyrae, the reliable heartbeats of the universe marking time and distance with such precision, we've used them to measure the expansion of everything. Some change because they're not alone, because gravity has locked them in partnerships so close they eclipse each other, steal from each other, sometimes destroy each other. Algol, RS Ophiuchi, Beta Lyrae. Binary dances played out in shadow and light. Some change because they're young and don't know how to burn steadily yet, throwing tantrums of brightness that flood their neighborhoods with radiation. T Tauri stars, Fu Orionis events, the chaotic adolescence of stellar life. And some change because they're old, because they're dying, slowly shedding their outer layers into space like elders letting go of everything they once held. Mira, Betelgeuse, the slow exhalation of giants preparing for silence. But beneath all these mechanisms, beneath the physics and the mathematics and the categories we've built to organize what we see, there's something simpler, something more profound. Stars change because change is the nature of existence. Nothing in this universe stays the same. Not planets, not galaxies, not even the vacuum of space itself, which quantum mechanics tells us is seething, with virtual particles appearing and disappearing in fractions of a second too brief to measure. Everything that exists in flux. And stars, those massive engines of light, burning across distances we can barely comprehend, they're no exception. They're not eternal. They're not fixed. They're alive in a way we're only beginning to understand. And their light, their variable, pulsing, sometimes unpredictable light, is the voice they use to tell us so. Think about what that means. Every photon that reaches your eye from a variable star has traveled for years, decades, sometimes centuries, through the emptiness of space. It left its star during a specific moment in that star's life, during a contraction or an expansion, during an eclipse or an eruption, during a theft or a shedding, and it carried that moment with it, encoded in its wavelength, its energy, its timing. And when it finally reaches Earth, when it passes through our atmosphere and lands on your retina or on a telescope's detector, it delivers a message, not in words, not in anything we'd call language, but in brightness, in change, in the simple fact that it arrived at all. And we've been reading those messages for thousands of years. At first, we misunderstood. We thought variable stars were omens, gods blinking, demons watching, the universe angry or pleased or warning us of things to come. But slowly, generation by generation, observer by observer, we learned to read more carefully, to see the patterns, to measure the cycles, to understand that the dimming wasn't supernatural, it was natural. That the brightening wasn't magic, it was physics. And in that understanding, we didn't lose the wonder, we gained it. Because a star that pulses according to the laws of thermodynamics and fluid mechanics and nuclear fusion is more wonderful, more beautiful, more deserving of awe than any demon or god we invented to explain it. John Goodrick taught us that darkness doesn't mean death. Sometimes it just means something's in the way. Henrietta Leavitt taught us that rhythm can be a ruler, that if we watch patiently enough, the universe will tell us how far away it is. Tabitha Boyajian and her team taught us that mystery is still possible, that even with all our tools and theories, the universe can surprise us, can do things we didn't predict. And that's not a failure of science, it's an invitation to look closer. Every variable star we've studied, every light curve we've recorded, Every observation submitted by an amateur astronomer at 3 in the morning in their backyard. Every gamma ray burst detected by a satellite. Every spectrum analyzed by a computer, they're all pieces of the same puzzle. And the picture that emerges isn't just about stars, it's about time, about change, about how nothing lasts forever, but also how nothing is truly lost. Because matter and energy don't disappear, they just transform, cycle, return in different forms. And that transformation, that endless recycling, is why we're here. The calcium in your bones was made in a supernova. The iron in your blood was forged in the core of a massive star. The oxygen you're breathing right now was created billions of years ago in a red giant that pulsed and swelled and eventually shed its outer layers into space. Those layers drifted, cooled, became part of a molecular cloud. That cloud collapsed, formed the sun, formed Earth, and eventually formed you. So when you look at a variable star, when you watch Mira fade and brighten, when you notice Algol dim and recover, you're not looking at something foreign. You're looking at family, at the process that made you. And if you listen carefully, if you quiet your mind and let the light speak, you might hear something familiar. A rhythm you recognize, a pulse that matches your own. Because we change too. Our brightness varies. Some days we shine, some days we dim, some days we're eclipsed by circumstances, by grief, by exhaustion, by doubt. And some days we erupt suddenly, unexpectedly, with energy and joy and creativity we didn't know we had. And that's okay. That's not failure. That's not instability. That's being alive. That's being part of the same universe that made Cepheids and Novae and Magnetars and Mira. The same universe that rewards patience, that hides its secrets until we're ready to see them, that teaches us over and over that the only constant is change, and change is not something to fear. It's something to watch, to study, to understand, and ultimately to accept. So, what happens next? Where do we go from here? The study of variable stars is far from over. We have better telescopes now than ever before. The James Webb Space Telescope can see stars forming in dusty nebulae, can watch young eruptive variables flare, in real time can detect the faint glow of Mira variables in distant galaxies. The Vera Rubin Observatory, set to begin operations, soon will survey the entire southern sky every few nights, detecting transient and variable objects by the thousands, maybe by the millions. We'll find novae we never knew existed, eclipsing binaries and configurations we've never seen. Cepheids and galaxies so far away their light has been traveling for billions of years. And with each discovery, the map grows, the picture sharpens, and the questions multiply. Because that's the thing about science. The more we learn, the more we realize we don't know. Every answer is a door, and behind every door is another question. Why do some FU Orionis outbursts last decades while others fade in months? What triggers magnetar starquakes? Can we predict when Betelgeuse will explode? What's really causing Tabby's star to dim? And beneath all of those specific questions is the deeper one, the one that drives everything. What is this universe we live in? How does it work? And why against all odds are we here to ask? Variable stars won't answer that final question, but they'll help. They'll give us pieces, clues, data points on a graph that someday might connect into something coherent, something beautiful, something that makes us look up and say, "Oh, I see. That's how it works. That's why we're here." And when that day comes, if it comes, we'll owe a debt to every person who ever looked up, noticed a star change, and wrote it down. From Hipparchus in 129 BC to the amateur astronomers submitting observations tonight. From John Goodrick, deaf and brilliant and gone too soon, to Henrietta Leavitt, underpaid and underappreciated and absolutely essential. From Tycho Brahe with his metal nose and his compulsive measurements to the modern scientists using machine learning algorithms to sift through terabytes of telescope data looking for patterns. looking for change, looking for the next mystery, and you're part of that story now. Because you've listened, you've traveled with us through time and space and variability. You've met stars that pulse, and stars that eclipse, and stars that erupt, and stars that steal. You've seen how chaos can become order, how darkness can reveal light, how something as simple as watching a star brighten and dim can tell us the size of the universe. And maybe the next time you're outside at night, the next time the sky is clear and the stars are visible, you'll look up and see them differently, not as fixed points, not as decorations on a dome, but as living, changing, breathing things, each one with a story, each one with a rhythm, each one connected to you in ways both literal and metaphorical. Next time you see a star, remember, it's breathing too. Somewhere out there, maybe in a way we understand, maybe in a way we don't, it's changing, pulsing, evolving, living its life on a time scale so vast it makes human history look like a heartbeat. But it's there, it's real, and its light, however faint, however far, is reaching you right now. Photons that left that star before you were born, carrying information, carrying energy, carrying proof that the universe is not empty, not dark, not silent. It's full of light, full of change, full of stories waiting to be heard. And that's what we've tried to do here, to listen, to tell, to share. Not with jargon or equations or complicated models, though those have their place, but with words that feel like breath, like the slow inhale and exhale of a star pulsing in the night, like the quiet rhythm of someone watching patient as the universe reveals itself one photon at a time. We've walked through neurons and dreams, through light and silence, through the eyes of people who saw what others missed, and the instruments that extended those eyes across the electromagnetic spectrum. We've seen that knowledge was never meant to be hoarded, only felt for a moment and then shared, passed forward, given freely to anyone willing to look up and wonder. And maybe that's the real lesson, not the physics, not the periods or the magnitudes or the spectral classifications, but the act of watching, of noticing, of caring enough to see when something changes and asking why. Because in the end, that's all science is: careful watching, patient questioning, and the humility to admit when we're wrong, when the universe surprises us, when a star does something we didn't predict, and we have to go back, rethink, recalculate, and try again. It's not about being right, it's about being curious. And variable stars with their endless surprises, their irregular rhythms, their refusal to fit neatly into boxes, they're the perfect teachers. They keep us humble, keep us watching, keep us wondering. So as we let this night settle back into stillness, as the stars continue their slow dances across distances, we'll never cross as Cephids pulse and binaries eclipse, and Mira fades and returns, and somewhere far away, a nova explodes in brilliance that won't reach Earth for 1,000 years. We can rest. We can close our eyes. We can let the weight of the day fall away. Because the stars will still be there, still changing, still shining, still telling their stories to anyone willing to listen. And if you've listened tonight, if you've stayed with us through pulsations and eclipses and eruptions and mysteries, if you've let the science become poetry and the poetry become understanding, then you've done something rare. You've connected across time, across space, across the vast distances that separate us from the stars and the small distances that connect us to each other. And in that connection, there's a kind of light, a brightness that doesn't come from fusion or accretion or magnetic fields, but from curiosity, from wonder, from the simple, profound act of looking up and caring about what you see. Thank you for drifting with us, for letting these quiet hours become a journey, for trusting that somewhere in the darkness between stars, there are stories worth hearing. And if you'd like to continue exploring the gentle mysteries of the cosmos, if you'd like more nights like this where science is told softly and sleep comes wrapped in starlight, stay close. There are more stories waiting, more wonders hidden in the quiet, more light to follow into the dark. Sleep well, dream gently, and the next time you see a star, remember, It's not just shining, it's changing, breathing, living. And in its light carried across unimaginable distances is a message just for you, that everything changes, that nothing lasts. And that's not sad, that's not loss, that's how light survives. That's how the universe remembers. That's how we, brief and small and fragile as we are, become part of something eternal. Good night, friend. The stars are still watching, and so are we.